Hi everyone, in this video I'd like to talk about functions. So I'll start with a function like the square root function, and when I write that I'm going to write f of x equals the square root of x. And so this notation here, f of x, it's very similar to what you might have seen in previous algebra courses, like y equals the square root of x. And I know from previous courses, if I were to graph this, I could make a little table of values, or maybe I know the shape of the function, but I know that when x is 0, y is 0, when x is 1, y is 1, when x is 4, y is 2, and so forth, and I can connect all the intermediate values. So I have an idea of what the square root function looks like. Now, what's different about our pre-calculus course is that instead of y equals the square root of x, what we're thinking about is f of x. In other words, I've got a function named f, and x is the input variable. In other words, this little variable that's inside the parentheses there, that is my input variable, or sometimes called my independent variable. And then this letter on the outside, the f in this case, that is the name of the function. So in this case, f is the name of the function. So I could have the c function for Kathy, or I could have the d function for, the denominator function. We'll often see f and g and things like that. But anyways, when we are graphing these functions, sometimes you'll see these exercises where they say, okay, f of x, we know what that looks like. It's the square root function. What would f of square root of x plus 3 look like? Or what would happen if I put the plus 3 underneath the radical? Or what would happen if I put the 3 out in front of the radical? How are these shifting left or right, up and down? So these are shifts. How is this function stretched? And then I can start introducing negative values and start thinking about reflection. So I could look at the square root of negative x, or f of x equals negative square root of x. So these are going to be some sort of reflections. And whether we're talking about the log function or the square root function, these general themes will persist. So let's take a look at Desmos and get an idea of what's happening, and then we'll come back and look at a logarithmic function. Okay, so I'm over here in Desmos, and I'm going to type f of x equals the square root of x. And there's my square root function. I could adjust the viewing window here by clicking on this little wrench, and I could maybe adjust my x-axis to go from, -2 up to 10, something like that. And now I can see the function a little bit clearer. So let's play around here. Let's take a look at a different function. What would happen if I graphed f of x equals the square root of x, and I'm going to put the plus 3 outside of the parentheses. So I can see what happened there is the function got shifted up by 3 units. So to keep these organized in my mind, I'm going to make my original function there a very dark, bold line. So I'm going to make this a color black, and I'm going to make the weight of that maybe 7, something like that. Okay, so we can see that's the original function, and then here is this little blue line is the shift up by 3. Now let's look at what happens when we put the plus 3 inside the square root. I'm going to zoom out a bit here. So in that case, it looks like my square root function was shifted to the left by 3 units. And you could come up with some hypotheses and say, oh, well, what would happen if I put a minus sign underneath that square root? You might think it shifts to the right by 3 units. So you can always go in Desmos and kind of shift your function around and see what impact that plus 3 would have on your function. Now, some other things that we could do, I'll remove those. Some other things we could do here, we could put a 3 in front of the square root function. And what that does is it's a stretch of 3. It's almost like I had a rubber band here and I kind of pulled it and expanded it. You can also think about a contraction if you had a number less than 1. Let's look at the effect of a negative sign. So if I put the negative inside the function, it's a reflection over the y-axis, and if I did a negative in front, it would be a reflection over the x-axis. Okay, so that gives us some ideas of what's going on. So we can see we had a shift. This first one was a shift up 3. This next one was left 3. The 3 in front there, that was a stretch by a factor of 3 or an expansion. This negative sign underneath the square root, that was a reflection, like a mirror image, over the y-axis. And the negative in front was a reflection over the x-axis. Okay, so now using the same idea, let's graph a different function. Let's take a look at the log function. So I'm just going to work on the same screen so that we see the patterns going on up here. So let's call this function g of x equals the natural log, so I'll write that ln of x. And the natural log function looks something like this. And if you don't believe me, we can go to Desmos and plot it. But before we go to Desmos, I would like you to consider, what do you think the graph of ln of x plus 3 would look like? Okay. Well, we know what the plus 3 out the back end did for the square root function. We might conjecture it does the same thing for the natural log function. Similarly, what happens when we put the plus 3 inside the argument of the function, ln of x plus 3? What happens when we put the 3 in front? Do we still get that stretching action? And then similarly, when we look at the natural log of negative x and negative natural log of x, do we see these same patterns? Is it still the reflection over the y-axis and the reflection over the x-axis? So let's go to Desmos and answer those questions. I'll get rid of all of these functions, and now I'm going to plot g of x equals the natural log ln of x. Okay, there's my function. It dribbles down towards negative infinity. Yeah, it gets infinitesimally close to the y-axis, or to the vertical axis, but it never touches it. All right, so let's go. Here we go. G of x equals ln of x plus 3. And indeed, we see it being shifted up by 3 units. Similarly, g of x equals ln of x plus 3. That's a shift left by 3 units. We could say g of x equals 3 ln of x. Again, it's an expansion by 3. We could think about ln of negative x. There's, again, our reflection over that y-axis. So yes, the same patterns still hold. So now what I'd like you to think about, suppose somebody walks up and hands you a function. So let's say, here's an example. Let's say somebody says, here's h of x. H of x is a new function called h, and our input variable is x. And it looks like 2 times the log, log, so this is a log base 10, of negative x plus 5. So some things that I would be thinking about here, since this plus 5 is out the back end, it's not tangled up in the log at all, it's just a constant added on the end. This is up 5. This is a shift up by 5 units. Since we have a negative sign inside the argument for the log, this is a reflection over the y-axis. And this 2 out in front, this is some sort of stretch or expansion by a factor of 2. So if my original function, let's draw x and y-axis here. If my original log function looks like that, and this point here is over 1 up 0. So I know that point 1 comma 0 is on my curve because when I plug x equals 1 and I have h of 1 equals log of 1, and I want to know what is that equal to. So let's see, log of 1, what is that equal to? It means that 10 to some exponent gives me 1. And that exponent must be a 0. So going back to properties of logarithms, if you want a review on that, let me know. There's some great Khan Academy videos on evaluating logs, or you can type it into your calculator. But the point is that 1 comma 0 is on the curve, and that's a great point to keep track of when I'm shifting up 5 units. 1, 2, 3, 4, 5. Right, we did that. Now I'm going to reflect over the y-axis. So now my curve has flipped over the y-axis. So let me at least get that curve down there. And now it's stretched by a factor of 2. So somehow I need to make it bigger. So let's go to Desmos and see how we did. Okay, I'm back in Desmos, and I'm going to type in h of x equals log of x. So that's my original function. I will change the color on this and make it a very nice heavy line so I can see clearly that was the original function. Now I will type in a new function. I have a stretch by a factor of 2. There was the log of negative x plus 5. And indeed, that's what we conjectured. So we flipped the line over, we shifted up, and then we expanded by this factor of 2.